With the smart card, you can actually design a variety of experiments for the same topic. For example, in the last video, we talked about they can just simply roll the card down the track and then use the data they collected to investigate the law of conservation of energy. But they can also have the cart start from the bottom and then have the cart going up and then investigate if mechanical energy is conserved during that process. So the smart cart has a plunger system. There's a button here. If you press it, the plunger will come out, then the car will be launched, and it'll help us do that. Okay, so we're gonna try that experiment and see if mechanical energy is also conserved during this process. So I'm gonna first pull out my app on the screen. It might take a second. And so again, it's a Spark View app. And view new experiment. Choose a layout, the first icon, and then make sure it's connected. I need to turn on the power. All right, now the card shows up. I'm gonna connect it, my phone to the card. Cancel update, done. All right, so position is here. All right, so again, I'm gonna use 50 Hertz instead of 10 Hertz. All right. So for this experiment, I'm only gonna care about the part where the card gets launched and reach to a maximum height. It'll come back down and get launched again. That part I'm not gonna investigate in this experiment, but I'll actually look at it in the next experiment. Okay, so basically it'll look like something like this. So, and then I'm just gonna look at the part where the card get the initial launch, then reach the maximum height. So I'm just gonna investigate this part for the law of conservation of mechanical energy. All right, so I'm gonna go ahead and start my app. At the same time, I'm gonna be launching the card. All right. So now let's take a closer look at the data. Let me turn off the audio first. So let's first identify the part of the graph that we're gonna look at. So this is a position time graph, and we're gonna look at when the position increase until it reaches the maximum height. And because after that, the car comes back. And as we mentioned, we're not gonna look at this part, so just this first part. And the corresponding, this is the corresponding VT graph. And we're gonna be looking at this part. So this is when the car reached the maximum velocity at the bottom after the plunger launched it. So you can see there's a sharp increase from in here in velocity. It's due to the plunger is launching the cart, right? Then it reached a maximum velocity. And after that, when the car travels up the slope, the velocity decrease at a constant rate. And again, I'm going to use a previous trial I did because I already analyzed it to save some time. So it's the same experiment. Right. So basically and if you look at the PT graph, it's a nice parabola as well. At this time, you can see the slope decrease, which makes sense because it's a decelerating motion. And the VT graph is a nice straight line with a negative slope. Again, makes sense because it's velocity is decreasing due to acceleration is down the slope. And basically, we're gonna pick 2 points as well during this process and analyze if the mechanical energy is conserved between the 2 points, like if the mechanical energy is the same. So I'm gonna pick a point basically just at the maximum velocity. And then let me check. So it's 2.08 seconds. The maximum velocity is 1.248 meters per second. So this is right after launch from the plunger. The maximum velocity it reaches at the bottom. And the corresponding position at 2.08 is 0.0691. So I'm gonna take a note. Later, I'm gonna use those for calculation. The other point I'm gonna pick would be at the maximum height at the top. Now this, I think it's 2.74 seconds, right? Because after that, it's 0.5333, which is smaller than that, 0.5339, and before that, it's also smaller than that. Okay, so this is the maximum height, 2.74 seconds, with the position 0.5339. So I'm gonna use those data to do some calculations. All right. So again, let me draw the slope first. And this time, the card goes from the bottom to the top. Okay. And again, this is a 10-degree inclination. But I didn't pick the initial point. I picked the point at t equals to 2.08 seconds with a position of 0.069 meters and with the initial velocity, which is also the maximum velocity it reaches on the bottom at 1.248 meters per second. And this point on the top time is 2.74 seconds, position 0.5339. And at the top, the velocity is 0. And in fact, on the graph, the velocity at 2.74 seconds is not exactly 0. It's about 0.015, but it doesn't really make a difference when you do the calculation. So I'm just gonna substitute, make it 0. And then, so I'm gonna calculate the mechanical energy at the bottom. So again, I'm gonna make this my 0 potential energy ground. So here, the potential energy is 0, and I'll call this 0.1, 0.2. So the mechanical energy equals to Ke plus P at 0.1. And since there's no P, just Ke and half V1 squared, Ke equals to that, which is equal to a half 0.245. That's the mass of the cart in kilogram. V1 is 1.248 meters per second. So that's the total mechanical energy at point 1 equals to 0.1908 joules. And then I'm going to look at the mechanical energy at point 2. So the KE is 0 at point 2 because the speed is 0. And PE is equal to mgh, which is equal to 0.245 times g at point 8. And now this h, I'm not going to measure it using meter stick or rulers. It introduces more errors. I'm going to use the relative position between 1 and 2 and a bit of trigonometry here to get the h here. So I need the hypotenuse of this right triangle. So this is a right triangle. And the bottom angle is 10 degrees. And the hypotenuse is 0.5339 minus 0.069, right? Because from the beginning to position 2 is 0.5339, and from beginning to 1 is 0.069, and the difference between them is the distance between 1 and 2, which is the hypotenuse. Then multiply by sine 10, give me the opposite side, which is the height of position 2. And then I get 0.1938 joules. And you can already see it's not a big difference. So they can tell the energy, mechanical energy, it's conserved, it's the same. And if they want to get a percentage error, they can just take the final value minus the initial and divide it by the initial. I'm going to put an absolute value around it to make sure it's positive. And the answer is 0.0157, which works out to 1.57% percentage error. So it's actually quite impressive how accurate the smart card is. So I'm gonna also talk about something that may be of interest to grade 10 honors. So the grade 10 honors students can think about the problem I'm going to talk about next. Okay, so if you have noticed, this is the initial energy at point 1. This is the final energy at point 2. It's really, really strange that the initial energy is smaller than the final energy, right? Because from point 1 to point 2, technically you can see there's a friction, there's air resistance, there's going to be some mechanical energy lost to heat energy, right? So the mechanical energy at point 2 should be smaller, not bigger than the initial mechanical energy. So what is the problem? Okay. So the grade 10 honors students can think about that. This is a really interesting thing to think about. And there's also a calculation they can try, because as we mentioned with the smart card in the beginning, there's also could be some stuff that's happening that you are not aware of that might affect the data. So we're gonna try, so instead of a point here, we're gonna pick another point up the slope, so a bit far away from the initial. Let's say, which point do we pick? We can pick, so instead of, so instead of 2.08, let's pick a point somewhere here where t is equal to 2.26, a little bit far away from the initial, because there's a plunger in the beginning, right? So it, and we'll actually talk about it later. So for now, let's just pick a point further up the slope. T equals to that, P equals to 0.2684 meters, and V equals to 0.963 meters per second. All right. Let's call it 0.3. And I'm going to use this point. So basically this point here. And 0.2 to see how their mechanical energy compared to each other. So I'll do a similar calculation as I did before. But this time, I'm going to make this my P0 to simplify my calculation. And literally, I'm just doing the same calculation here, but with a different set of data. So I'm going to quickly do the calculation here. So the mechanical energy at 0.3 would be, the potential energy is 0 because I made it 0 potential energy, and it's just going to be kinetic energy, which is a half times 0.245 times the speed 0.963 squared equals to 0.1136. And the mechanical energy at 0.2 is going to equal to 0. There's no kinetic energy, so just gravity potential energy. But now the height is going to be 0.5339 minus 0.2684 times sine 10. Right? So it's going to be this height because I made this my 0 potential energy reference ground, and this height is equal to sine 10 times the hypotenuse here, which is equal to the difference between the position at 2.26 seconds and the position at 2.74 seconds. And from there, I get 0.117, 1107 joules. Now, this makes sense, right? Because this is the mechanical energy at 3. It's greater than the mechanical energy at 2. Right? Mechanical energy at 2 is 0.1107. This is 0.1136. And it makes sense because at 3, and when it travels up, mechanical energy will be lost to heat, and the total mechanical energy should decrease a little bit to 2. But how come number 1 is smaller than number 2? The mechanical energy at 1 is smaller than mechanical energy at 2. So what's going on in the beginning that kind of makes this really strange thing happen? So it seems like the data at 0.3 is fine. So you can think about it. Okay, now this is my thought. So I want you to take a closer look at the plunger system of the cart. So let's say this is the stopper at the end. And So the plunger, this is the cart, and the plunger is inside, okay? And then when the plunger launches, it'll push the car up the slope, right? So the plunger comes out a bit, and then the cart goes up a bit. And this is when the plunger fully released. This is when the plunger fully released. And then after that, the car will just go by itself. Okay, so the problem happens at the point when the velocity reaches the maximum. It's not at when the plunger is fully released. It's a little bit before that. Okay, so that's where the problem is. Okay, so I'll make it more clear. So if you're looking at the cart, when will the cart accelerate upwards and the velocity increase? It's when the force up the slope, which is from the plunger, let's call it the tension force of the plunger, Ft, it's greater than the force down the slope. What are the force down the slope? There's friction, including air resistance, and there's also this component down the slope from gravity. So this component from gravity down the slope. Okay. Sorry, bad drawing. So gravity, you can decompose it into let me draw it. This is gravity, mg. It's in the vertical direction, and you can decompose it into down the slope and pressed against the slope. Okay, so this component of gravity, you can call it Fg parallel, combined with friction, is our down the slope, and Ft is upslope. So when Ft is equal to the magnitude of Fr plus Fg parallel, that's when it will reach maximum velocity. And beyond that, if Ft becomes smaller, then V is going to decrease. Right? So, and we talked about at t equals 2.08 seconds, V is maximum, right? But at that point, the plunger, the spring in the plunger is still compressed. It's not totally back to the equilibrium position. So that's why you still have the Ft here, right? So the plunger, if you imagine it as a spring, so it's still like compressed. I'm gonna use a different color. So the plunger is still compressed. It's not fully stretched, okay? It's not like in the equilibrium position means the spring is like no force. It's like in its normal state. It's not compressed or stretched. But now when it reached the maximum velocity, the plunger is still compressed. So for example, if this is the normal position, this normal position is a bit longer, and the plunger is still compressed. That's why it has this Ft equals to Fr plus Fg parallel. And that's when the velocity reached maximum. So past that point, so past the 2.08 seconds, the velocity will decrease, and then the plunger will start to go back to normal. But between here and here, you can see between the let's say this is 2.08 seconds, and let's say this is whatever time, it's going to be very close to 2.08. But there is this period of time when the plunger is still working on the cart, and that's still increasing the total mechanical energy of the system. Although it's a really short period of time, but it's doing it. Okay. So it's going to be a problem if we here, if we look at our calculation here. Yeah. When we calculate the mechanical energy at point 1, we only consider the kinetic energy, but this mechanical energy actually changed over time, although a really short period of time, which is mentioned, right? So maybe from 2.08 to 2.09, because the plunger is still doing work on the cart, the total mechanical energy is going to be increased. So it's not going to be equal to that. It's going to be equal to this plus the work done by plunger. So this should be the total mechanical energy. And that's why at the top, when you calculate the total mechanical energy, it appears to be greater than the total mechanical energy here. It's gonna be, because you didn't consider the work done by plunger. If you consider the work done by plunger, you add them up, then the energy is gonna be bigger than the energy at the end, because there's also some energy that lost to heat. So the heat energy actually comes in here, and then all the numbers will be balanced. Okay. So again, the reason you have the initial mechanical energy smaller than the final mechanical energy, which is totally counterintuitive, is because this is not the initial mechanical energy. Because at this point, 2.08 seconds, so we use 2.08 seconds, the velocity in that time, the plunger is not going back to normal equilibrium state yet. It's still compressed. And so in the next split of second, that compression is doing the work on the cart, which increased the total mechanical energy. Okay, so you have to pick a point, like for example, 2.26 seconds, a little bit far away from the 2.08. And that's when you have the work already being done converted to mechanical energy. So from there, that's when no external force is doing the work to change the total mechanical energy of the system, and then mechanical energy is conserved. Okay, so this ties in the work energy theorem we talked about in physics 11, work energy theorem. So work net is equal to dot Ke plus dot Pe. If there's no work, external force doing the work on the system, then W net is 0. Then there's no change in P and Ke, right? And P is a P initial, P final minus P initial. Dot P, right, is equal to P final minus P initial. Dot Ke is equal to Ke final minus Ke initial. And then you move initial to the left. So you have P initial plus K initial equals to P final plus K final. And see, you can derive the law of conservation of mechanical energy from work energy theorem. But that's when the network is the work done by external force. If it's 0, and then you have the mechanical energy conserved, right? But in this example, at the beginning, the plunger is still doing the work on the cart, even past the 2.0 seconds. It's still doing a little bit of work. So that will increase the total mechanical energy here. So the total initial mechanical energy is actually increased a little bit beyond 2.0 seconds. And then after the plunger is not working on the cart anymore, that's when the mechanical energy starts to be conserved. Okay.